Welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Cathy, who is an assistant professor at MIT. Where she's part of the Civil and Environmental Engineering Department, leads an IDSS. Something about Cathy: she obtained her Bachelor of Science and Master of Engineering from MIT, and then she moved to the West Coast, where she obtained a PhD from UC Berkeley. And all of her studies were in electrical engineering and computer science. She then was a postdoc at Microsoft, and her research interests are at the intersection of machine learning, decision making, and mobility. Currently, she's focusing on how learning-based methods can advance emerging mobility systems by better coping with the complexity of decision and control. In general, she's interested in enabling policy-relevant research by pushing boundaries of learning, control, and optimization. As you have seen, the research has been featured in a number of dissemination venues, but also she received a number of awards, the most important recently the NSF Career, and I'm very excited to hear more about the topic. And today she's going to talk about intelligent coordination for sustainable roadways. Go ahead, Cathy. Pleasure.
Thank you. Thank you so much, Joella, for hosting me and for the kind introduction. So I'm going to share a bit about my what my lab has been up to in the last few years. But before I jump into it, I like to talk a little bit about sort of what gets me up in the morning, which is really problems that have the potential to leverage emerging technology while improving people's lives, while working on interesting technical problems. And so this, I find, coincides pretty well with the areas and research communities that I interact with, those being autonomy, specifically for roadways, the intelligent transportation systems, which we often rely on every day, as well as learning for decisions and control. So because it's very easy to take for granted something that we use and rely on every day, that is roadways, let me remind you that roadways are the circulatory system of the economy. They link producers to markets, they link workers to jobs, they link students to schools, and they link the sick to hospitals. At the same time, they are not perfect, as we know, and rather they are far from it. So one of the main approaches that we've been taking over the last 20 years to improve roadways has been autonomy. This is the idea that if we can achieve autonomy, then vast societal benefits will be unlocked. The reasoning goes something like this. Let's build perception, let's figure out planning, common sense reasoning, social orientation, altruism, and potentially a few other components. And then we can leverage this to attain more sustainable roadways. Here, I'll focus on safer, cheaper, cleaner mobility, but it could mean a variety of other good things as well. So as you may know, as evidenced by this sort of not happening, us not seeing very much of autonomy on the roadways, this has been harder than we thought. So let me review sort of how we came to this point and where we go from here. So I'm sure many of you have seen this before. This is the Gartner hype curve, which describes the life cycle of a technology, which includes the hype stage, which is the peak of inflated expectations, as well as what happens before, sort of the innovation trigger, as well as what follows the trough of disillusionment. So let me recap now this wave of interest in roadway autonomy. It's not the first, and it may not be the last. So this wave sort of kicked off with the DARPA Grand and Urban Challenges in the mid-2000s. About a decade later, we see articles of this nature. This is from Business Insider, titled "Wide Adoption of Self-Driving Cars Could Be Only 5 Years Away." Okay, it's been more than 5 years away after that now. So this was followed shortly after in 2018 by the very unfortunate crash of the Uber self-driving vehicle, which struck and killed the pedestrian Elaine Hertzberg. So causation or correlation, I don't know, but this coincides roughly with the dip in hype into this trough of disillusionment. And this is roughly where we are now. So I want to take a moment to review the rationale for roadway autonomy, why we thought this was a good idea, because it really does have its merits. So the most prominent rationale for roadway autonomy is safety. So there were about 43,000 fatalities on US roadways in 2021. And this number is not going down despite all of our improvements to vehicle safety. A very famous study from NISTA concludes that human error is involved in around 94% of these fatalities. And therefore, it is really hard to conceive of an approach that would get us to zero deaths or anywhere near zero deaths without removing the human from the equation. The second motivation is time. So I don't know about you, but I could really use a 25th hour in the day. Various studies show that Americans spend about an hour on the roads each day. And travel time is by far the largest component of cost in the sort of in the cost of moving people and goods throughout the country. So, we might think that, if we wanted more time, we could hire more drivers, have us all driven by taxis, but that is exceedingly expensive. And so autonomy could potentially give us back our time while reducing that cost. A third motivation, and there are many more, is the environment. So the transportation sector is the largest contributing sector of greenhouse gas emissions in the US at around 29%, and a vast majority, roughly 80%, are on roadways. So autonomy could enable all sorts of efficient use of vehicles, including sharing of the vehicles, de-emphasizing performance, platooning, integration with public transit, accelerating electrification. I could sort of go on and on. Okay, so unfortunately, this has not really panned out, at least yet. And the reasoning, the place where the reasoning fails is that it's not clear if we can, achieve the sort of first part of this reasoning. So achieving sustainable roadways seems to require a different approach. So for lack of a better term, I'm going to call this use-driven design. And the alternative reasoning goes something like this. Let's consider first why we want to improve roadways, how we want to improve them, and then let's actually design for that. So let's flip the reasoning. Let's start with sustainable roadways on the left and see what does it actually require. Does it require autonomy, or is autonomy sufficient but not necessary? So this talk, I'm going to talk about a relaxed notion of autonomy. I'm going to talk about the ability to coordinate vehicles and consider whether this is sufficient to move the needle on sustainability for roadways in terms of cheaper, safer, and cleaner mobility. The reasoning to tie this back goes a little bit like this. For us to coordinate vehicles, we might not need every aspect of what is required to build full autonomy for vehicles. But with a relaxed notion of autonomy, this may be more near-term achievable while seeing some of the benefits that we seek for the system. So here is the outline for the rest of the talk. I'm going to consider one at a time how intelligent coordination could make safer roadways, cheaper coordination, and cleaner roadways. As a bonus, I'm going to talk about how these intelligent coordination problems are unfortunately annoyingly hard to solve, and how we might go about designing more methods that are more effective. So let's start with the first one, which is about cheaper coordination. So this is joint work with my students, Jung-Hoon, Siri, Mary, and my collaborator, Roy Dang at UIUC. And this work is based on two sets of works pertaining to average case performance analysis as well as worst case stability analysis. For the sake of time, I'm going to focus on the average case performance analysis. So the premise of this section is really that there is a very cheap way we could potentially coordinate vehicles, which is to give drivers a smartphone app. We basically all have smartphone apps in our cars. So let's put this in context of autonomy. So autonomy ranges from level 0, which is fully manually driven cars, all the way to level 5, which are fully autonomous cars. A smartphone app that guides human drivers based on, for instance, some speed set points that change over time could be considered something like level 0.5. It doesn't require any modification to the vehicle. We might think of this as possibly the lowest cost near-term form of autonomy. And why might we be interested in this? So what we know from our work as well as others over the last few years is that with full autonomy, with full autonomous vehicles, it is sufficient to even have a few of these vehicles in a mixed traffic setting actually improve roadways in terms of travel time, in terms of throughput, in terms of fuel. So a small fraction of vehicles like 5 to 30% can lead to say 13 to 120% improvement in various scenarios that you see in this video here. The question is, rather than whether level 5 vehicles are sufficient, we want to know if they are necessary to achieve these system level benefits. So this leads us to consider this problem, which we think of as coarse grain control. The question is, to what extent are guided human drivers capable of achieving the same traffic optimizing behavior of autonomous vehicles? You can think of the guidance as some kind of personalized dynamic speed limit or acceleration limit. Okay, so human drivers are still responsible for not crashing into cars in front of them just because the speed is set at some point. So we're going to consider a very simple model for analysis purposes of coarse grain control. So you can think of this as really piecewise constant guidance. This is also known as zero order hold with a hold length of some delta seconds. So we're going to hold some speed for some amount of time, change that speed, hold that for a bunch of time, change that speed, hold it for a bunch of time. And the goal is to design these coarse grain control laws denoted pi sub delta. And the question is, how coarse of guidance can still achieve this traffic optimizing behavior? We can think of delta as holding the guidance for something like 0.1 seconds, which is going to be our model of an autonomous vehicle. Humans cannot do this, or all the way up to holding instructions for 40 seconds. At some point in the middle here, humans start to be capable of following these instructions. And this is sort of arbitrary, but based on human factors research, there's some indication that roughly around 8 seconds, humans start to be able to follow such guidance. But I'll say we're initiating our own user studies to confirm this for our setting. Okay, so to be a bit more specific, we're going to consider a traffic scenario with a fraction row of guided vehicles and a fraction 1 minus row of unguided vehicles. Keep in mind, all vehicles in the system are human driven. It's just that some are guided based on the control law pi sub delta. And the main idea here is that the guidance here is updated every delta time. The actions of the unguided vehicles follow some conventional driving model. We'll consider a variety of traffic scenarios. And so each combination of the guidance type, the hold length, and the traffic scenario yields its own multi-agent control problem. The approach that we're going to take is we're going to learn these coarse grain control laws for these various scenarios and also for different delta using deep reinforcement learning. We're also going to analyze the stability of the coarse grain system. So I'm going to jump right to the results, and I'll come back and talk about some of the methods. So let's consider this very simple setting. This is our model highway. It's a circular track. This is sort of like the cart pole of traffic. You would want your work to sort of work on the simple system before you consider more sophisticated scenarios. There are a few nice things that we can say about this, and a few insights. So the coarse grain guidance actually coincides with what's called sample data systems. This allows us to leverage a framework known as the Lyapunov-Krasovsky functionals to actually derive sufficient conditions for system stability. That's all I'm going to say about that. I'll refer you to our papers for more details. The other nice thing about this problem is that it is an easy problem in a certain sense. This system has a fixed optimal velocity. So in principle, we should be able to hold the guidance for arbitrary amounts of time, and it should be fine. So on the x-axis here, we see the guidance hold length. And on the y-axis, we see the performance measure. This is the average velocity for this system. In general, we would expect some high performance where the optimal curve is, and we would expect this to eventually dip, okay, in general settings. But in this setting, we expect a flat line at the top, okay, much higher than the baseline in green. So we do indeed see this for speed guidance. However, for acceleration guidance, we see some sort of messy curve here in terms of performance. So this is actually very problematic for us from a optimization standpoint. Once we've cleaned this up, and I'll sort of tell you about how we do that in a little bit, we actually see that the performance can be much higher than sort of naive training. This actually hints at some brittleness, because the jagged red curve is trained using vanilla deep reinforcement learning, and this hints at the brittleness. So keep in mind that each problem here, each different guidance hold length, sort of 1 second at a time, these are all treated as independent reinforcement learning problems. And they're essentially very similar to one another. This problem are very, very similar. And yet we see very different performance outcomes from vanilla training with hyperparameter tuning and everything. So this brittleness motivates us to develop a method which we call the temporal transfer method. This is the idea that for some target hold length, we may be able to train a control law in a similar setting and then transfer the outcome to this setting. Because these problems are all essentially the same. The only difference is the hold length of the instruction. And so the structure that we leverage is basically that coarse grain problems are easier to solve because they have a shorter effective horizon. However, these coarser problems may be suboptimal because the instructions are coarser. So the idea is for a target hold length, there's a sweet spot where the performance is still good, but the problem is easier to train. And we can essentially identify this through a stochastic form of binary search. So leveraging this idea, we're able to train more reliably for more sophisticated settings. So here is a highway ramp setting, and in red is the vanilla training curve without the method, and in blue is applying our method now for acceleration as well as velocity guidance. And so the outcome here is that compared with some baseline, we see that we do retain the traffic optimizing behavior. There is, of course, some degradation, some graceful degradation, but we do actually retain it quite a bit into this human compatible region. So the contributions here are that coarse grain guidance does preserve benefits from autonomous vehicles in terms of speed, fuel, and throughput across a variety of traffic scenarios. The implication is that guided human drivers could enable this kind of low-cost, near-term autonomy on roadways. We find that vanilla deep reinforcement learning is brittle to even these minuscule changes in the environment, such as the action duration, and that the temporal transfer learning method improves the reliability of learning these coarse grain control laws. So because of this, this motivated us to dig a little bit deeper, because we changed the problem a tiny bit, and these state-of-the-art off-the-shelf methods no longer worked, and thus we were unable to analyze our problem at first. So I'm going to mention a couple of works now that are recent, and they are also done jointly with my students, which is really motivated by this brittleness that we see here in this coarse grain control application. So what we were curious about is this a problem with our use of reinforcement learning? Is it unique to our problem, or is it the tool? Is it a property of where the reinforcement learning methods are today? So this led us to look for this issue in existing deep reinforcement learning benchmarks. And for better or worse, we did find this brittleness. So first, staying close to home, this is a traffic signal control benchmark. So this controls traffic signals, not cars. And this is a recent benchmark which considers both non-learning methods, classical methods, as well as learning methods, all reinforcement learning based. And so what we did is we wanted to consider, okay, what if we twiddle these environments a little bit? Will we see this brittleness? So what we did was, as part of actually a different project, we modeled sort of hundreds of scenarios based on Salt Lake City in collaboration with the Utah Department of Transportation. And here you see some statistics of the intersection scenarios. And then what we did was we took these methods, we took each one and we reevaluated them. We retrained them one at a time on each of the environments here. And we wanted to see the overall success. So what we find is that although in the reported benchmark, this RESCO benchmark, a number of learning-based methods outperform fixed time control, which is probably the most widely studied form of classical approach to traffic signal control. When we reevaluate under our set of what we call natural variations, the learning methods no longer outperform the classical methods. Okay, so this hints at a certain kind of brittleness. We then look at these we do a similar procedure for some popular control benchmarks, and we actually find similar findings. It's not as outrageous as flipping between learning and non-learning methods, but it sort of flips the order of different learning methods for these benchmarks. Or goes from the learning methods can solve them reliably to they cannot solve the problem reliably. Okay, so this is not good news for pure learning-based methods for decision-making, in the sense that it appears that they are not robust to these natural variations. At the same time, these pure learning methods are motivated by how rigid model-based methods can be, which is another form of brittleness. So this motivates us to consider a hybrid approach. So can we get the best of both worlds by leveraging known problem structure in a model-based manner while providing flexibility for the difficult to model aspects in a model-free manner? It would be nice to be able to systematically study this problem. Something like an ImageNet for decision-making would be wonderful. For control problems, it'd be wonderful. We don't have something like that yet, not in a sort of real-world context, but we could potentially, for the time being, fake a data set by looking to discrete optimization. The discrete optimization community has decades of detailed specifications of decision problems with all of its natural variations. Here's an example which is, again, close to home, having to do with vehicle coordination, and this is the vehicle routing problem. So this, you can think of it as Amazon's package delivery problem and all of its variations. So this problem in particular has been studied for some 60 years, and there's a very nice diagram which shows the basic vehicle routing problem, and then its sort of family of variations, depending on whether the vehicles have capacity, whether there are dynamic demands, whether there are time windows for the deliveries, whether the vehicles are electric, and so on and so forth. So this gives us a sort of data set of problems, of decision problems with their variations, from which we can start to devise these hybrid methods. So the hybrid method that we're going to consider leverages the model-based backbone of large neighborhood search. So this is an algorithm that basically leverages the idea that large problems can often be decomposed into smaller problems. It works by taking this large problem and then seeking better solutions by re-optimizing subcomponents. So for instance, we might select this as a subproblem. We will re-optimize it using a solver. We assume that we can solve a small problem, or at least we can, suboptimally solve a small problem. And but we cannot solve the larger problem. Okay, so we can re-optimize this small problem and plug the new solution back into the larger problem, and then we can iterate. So typically these subproblems are selected randomly or according to a heuristic, which is then again specialized to the specific variation of the problem. So instead of that, we take a data-driven approach to learn the subproblems to select. And this procedure can then be used to automatically tailor to variations of the problem. So I'm skipping all of the details here. Basically, it's a neural network, it's a transformer model, we formulate a regression problem, and I'll jump right to the results, which is basically that this leads to a 2 times speed up over random selection of subproblems. So these curves right here already yield an improvement of almost 10 times just with large neighborhood search. And then basically we can improve it by another 2 times with learning. So this is studying a fairly large problem for the most widely studied variation of the vehicle routing problem, which is this capacitated vehicle routing problem. We can then apply the same algorithm to variations of the vehicle routing problem. Here is with time windows, and here is with both pickups and deliveries. And we can see again that our method yields a further improvement beyond random selection of subproblem. And this indicates that the algorithm is able to automatically identify tailored selection strategies for these different problem variations. So in short, we find that deep reinforcement learning fails to be robust to natural variations. These small deviations in the action duration, signalized intersection layouts, as well as the standard control benchmarks. The method we propose is called Learn to Delegate, which is this neural guided large neighborhood search. We find that to be more reliable to natural variations of the vehicle routing problem as compared with random selection. We're now extending this work and these ideas to consider different applications. So we're working with Amazon Robotics to consider this multi-agent pathfinding problem in robotic warehouses. We are considering different subproblem types, such as the type of neighborhood rather than the neighbor within the neighborhood, and also different algorithm backbones, such as branch and cut for solving mixed integer linear programs. So back to the main theme now, I want to talk about cleaner roadways. So this is by far the largest project I have undertaken. It is done with a big team of students. It is still ongoing, but I'm very happy to share with you some preliminary results. This project is split roughly into a few modeling components as well as a few control components. So as a reminder, we urgently need to decarbonize transportation. It's a big problem. And coordinating vehicles, we would like to understand if this can help. So the specific opportunity that I'm interested in has to do with how traffic signals induce stop and go basically everywhere and all the time. So about 50% of vehicle miles traveled in the US are near signalized intersections. And according to a recent survey on whether we can mitigate emissions, a very, very coarse meta-analysis was I took all the studies reported in this survey and I took the plus and minus 1 standard deviation. This gives us a range of about 6 to 28% of avoidable CO2 emissions from the excess acceleration deceleration. If we're optimistic, sorry, I should say what I'm doing here is this was a back of the envelope calculation that was very informative for when I was getting started in designing this research problem. If we're optimistic, we can take the upper range of this standard deviation and say, okay, roughly 15% of CO2 from driving could potentially just be wasted at intersections. This is maybe something we should be looking at. So just to be a little bit clear, here's an intersection simulation. You can see that there is queuing at the intersection, okay, the yellow cars. In contrast, we can look at this intersection with a form of eco-driving. So this is giving some guidance to the cars such that when they get to the intersection is green. And so you can see that the cars are sort of slowing down a little bit prior to the intersection, and there is much less queuing at the intersection. Okay, so this is the problem. Would coordinating vehicles to reduce CO2 emissions at intersections actually move the needle on climate change mitigation goals? So there is actually a very vast literature on related work. This is called eco-driving at signalized intersections. There are some 50 supportive studies that say this is a pretty good idea, but we don't see it in practice. And my question a few years ago when we were starting this work was, why not? And so the gap that I was very curious to fill was many of these studies look at how to eco-drive. How do you eco-drive on this intersection with this kind of technology, with this kind of method? But rather, I want to look at, should we eco-drive? Should we do this at scale in particular? So in order to answer this question, we want to estimate the expected improvement of eco-driving over possible driving scenarios. So as a tidbit, as I was doing some literature review, I found this article, this first reference here, which is titled Eco-Driving, an Overlooked Climate Change Initiative from 2010. This is actually focused on highways rather than intersection scenarios. But here you do see today in many cars, there's this eco mode that's optimizing driving for highways. And so potentially, if we figure out something here, maybe we can see a similar analogous climate change initiative into the future. Okay, so the central challenge of this problem is really the diversity of traffic scenarios that we have to consider. So first of all, intersection layouts are all different from one another. You can see that there is some number of lanes, some number of approaches, and different turning restrictions for different intersections. And these are just variations that I can, show pictorially. There's also the grade of the road, like the slope of the road, the weather conditions, the travel demand, the vehicle types, and age. So this leads us to many, many scenarios that are possible. And there indeed are many scenarios, sort of millions, possibly billions of scenarios that we would have to consider in order to really take an expectation over the effectiveness of eco-driving. So let me summarize the challenges a little bit more concretely. The first challenge is that eco-driving controller design has focused on specific scenarios. There's no known approach that can simultaneously handle all the considerations that we need to really take this expectation. There's also no known approach that scales to analyzing millions of scenarios. So the approach that we're going to take is one of multitask reinforcement learning. The second challenge is that large-scale modeling of traffic, at least that is available to academic researchers, has focused on highways. And so the approach that we are taking is to model at large scale urban traffic, as well as other eco-driving factors. So we have to do the second problem first. It's quite unfortunate. We have to do this large scale modeling. In order to do this at scale, we leverage OpenStreetMaps. If any of you have worked with OpenStreetMaps, you know how wonderful it is. You also know how terrible it is. Almost all the quantities, all the attributes are missing. We need things like the length of the lane, the speed limits, the turn lane configurations, the lane counts, the road grades. The vast majority of these quantities are missing. So we developed a data imputation methodology. We did some validation. It's not perfect. It is much better than not having the attributes. We leverage this to model 10 major cities across the US, also based on our partnerships. I mentioned Utah earlier. And in general, we selected large emitting regions in the US. And this, for reference, this leads to about 30,000 intersections. This is about 10% of the signalized intersections in the country. We would love to do more, but we're a small academic team. These are also only the static factors. We also need to consider non-static factors. So for instance, the different scenarios, different percentages of guided vehicles, different seasons, different weather conditions, different traffic demands, depending on whether it's during peak hours or off-peak hours. Okay, so this leads us to about 1.5 million scenarios with others that we are still formulating. So this is one aspect. We also have to connect the dots. I'm not going to belabor this. I just want to give you a sense of there's a very large modeling effort that we underwent to go from all the factors that affect eco-driving to the final outcome. I want to just highlight that, the static factors are just a small piece of it. The non-static factors are a much larger piece. And what really allowed us to actually do this work as a small team is that many of these factors are already available in an industry standard tool, which is provided by the EPA, the Environmental Protection Agency, and the tool is called MOVES. It is an industry standard emission model that captures everything. I mean, almost everything. So, for instance, you can provide the season, you can provide the weather conditions, you can provide the humidity, you can provide the age of the vehicle, the type of the vehicle, the fuel type, and it will tell you the emissions for a trajectory. This is a wonderful tool. It is not very slow, but it is too slow for our problem, where we really need to analyze millions of scenarios. So rough back of the envelope calculation indicates that we need something like 9 compute years to run the analysis once. So the solution we take was, okay, well, we reason that underlying this tool is a bunch of functions that look like this. Emission functions are smooth, continuous functions. So what we did was we reverse engineered this tool, which is this extensive Java program, and we learned neural surrogates as well as other kinds of functions, polynomial functions, decision trees, to approximate the inner workings of this emissions model so that we could expose these different, the richness of what's underlying, but we can actually accelerate its application. So that is what I'll say about modeling. Now moving on to control. To keep things simple, because the problem has been complex enough, we are only considering the acceleration of the vehicles. The vehicles do lane change, but not in an eco-driving way. The vehicles around, the surrounding vehicles, they lane change and everything. We're just only optimizing for acceleration. And I'm also glossing over a number of other modeling choices and assumptions that we have made. Okay, so now we take a multitask reinforcement learning approach. The general idea of multitask reinforcement learning is that, okay, well, every time we train, or every episode that we train, we'll use a different task drawn at random. Here, a task is a traffic scenario variation drawn from the 1.5 million scenarios. The observations to the agent will now include not only the typical vehicle observations, but will also include a context vector, which has to do with the task, so that the agent can differentiate between these different tasks. But potentially there's some continuity between the tasks to make the learning more tractable and to share the experience across tasks. Our training procedure is pretty standard in terms of the algorithm, the architecture, and the training protocol. We use a shared parameter multi-agent reinforcement learning setup. The one non-standard aspect is that the reward function does require extensive design. We wrote a whole paper that is just dedicated to the reward function design for this problem. It is very non-trivial. So this works okay, not perfectly. And one small tweak that does make this work much better is what we're calling multitask reinforcement learning. This is simply multitask on a partition of the task space. It makes sense, I think, that a single policy would not be able to train perfectly on, on over 1 million scenarios. But we still don't want to train that many policies because that will hurt us from a scalability perspective. So we do a simple partition based on the number of lanes as well as the number of phases in the traffic signal plan. So this yields around 7 policies, which is still much less than the 1.5 million. When we assemble the final set of control laws, we can actually use the best policy for each scenario. We don't have to stick with the policy that was trained for the partition. Okay, so now moving on to the results. So this is preliminary. This is the first city that we're analyzing, but just to give you a sense of what we're starting to see, this is Salt Lake City, and at 100% adoption, what we see is something like 11% reduction in fuel. If we were to do a simple scaling from here all the way to the country level, so we have to make some distributional assumptions, this leads us to something like a 1.5% reduction in overall US CO2. And this is approximately equivalent to 60% of US flights. So to put this into perspective, The venture fund led by Bill Gates, what they are seeking as a gold standard is strategies that have the potential to reduce global greenhouse gas emissions by 1% by year 2050. So this, what I can say is that this appears to be in that ballpark. Another thing that we can analyze is the partial adoption. So here for 20% of adoption, we see about 0.4% reduction in US level CO2. This gives us about 20% adoption gives us about 28% of the benefits. So there's some nonlinear effect. The rationale, I think, is quite intuitive. If a vehicle is eco-driving, the vehicle following it might also benefit even if it is not following certain instructions. Okay, so in summary, eco-driving at signalized intersections could substantially contribute to transportation decarbonization. We've done extensive development of urban traffic models for about 10 cities to fill a gap in traffic modeling beyond highways. We've also devised these neural surrogates of the industry standard emission model EPA moves to accelerate and broaden access to diverse emission models. And this multi-task reinforcement learning allows us to actually analyze over 1 million eco-driving scenarios. So the last piece that I'll touch on, and I'll be sort of brief on this, has to do with safer roadways. Yeah, and this was actually very recently published. This was only put online maybe 3 weeks ago, and this is done with jointly with 2 of my students. So let me first talk about why safer roadways is such a hard problem. The answer really boils down to the bar being very, very high. So humans are incredibly safe drivers, even though there are a lot of fatalities. Both can be true. So the average is that we see about 80 million miles between traffic fatalities. This includes our drunk drivers, our elderly drivers, and everything. This is incredible. This is 8 nines of reliability. This is 8 nines following the decimal point in terms of failure-free miles driven. To also put this into perspective, we use AWS for our research sometimes. AWS offers about 2 nines of reliability. My Roomba offers about 1 9 of reliability. Where are our autonomous vehicles? So the answer is it's really hard to know because we haven't even driven that many miles. So this is Waymo in 10 years has driven about 20 million miles. And many of them are not driverless. Many of them have a safety driver. So the best estimates are that autonomous vehicles right now are anywhere between 2 and 4 orders of magnitude below the reliability of human drivers. I would claim that without some major breakthroughs, we really need to think about the problem differently. So we're going to take inspiration from air traffic control. We call it autopilot, but there are no autonomous aircraft in commercial aviation. There are 3, pilots in the cockpit. There's air traffic control on the ground. So let's bring in some of those ideas. Let's bring ideas from air traffic control to the dense traffic on roadways. What we would like to do is we would like to complement the autonomous capabilities with remote supervision from expert operators. It makes sense that we would like to borrow from air traffic control because this sector has an even higher safety record than roadways, 10 nines of reliability rather than 8. So we're going to look at a very specific question in this area, which we call the scalability of supervision. So suppose we took the driver who's currently in the car. Right now we have one supervisor, one operator for one vehicle. Okay, so it's a 1-to-1 ratio. Let's imagine, and let's make many assumptions, that we can take the driver and simply put them into a call center with steering wheels. Everything is like driving in the car. Communication is perfect. Sensing is perfect. And the question is, if we were to do that and we have some autonomous capabilities, then how many operators do we need to provide the same levels of reliability for driving on roadways or higher? Does it still need to be one-to-one? Because if so, we only made the problem worse by requiring communication infrastructure. So we're going to look at this problem by formulating a queuing model. And the way this is going to work is we're going to think of risky events that for which we want a remote operator supervisor. We're going to think of arrivals as risky events, and we're going to have these remote operators that can serve these risky events. And once the events are supervised, then the risky events leave the queue. This can be thought of as a queuing model with no buffer, as in the capacity is equal to the number of operators. What is our quantity of interest has to do with the probability of service loss. This is the probability that we cannot guarantee service. This is the probability that the system already has M risky events that are being supervised. If another risky event were to arrive, we could not guarantee its service. Reliability we can think of as then 1 minus P sub M. Okay, and now we can set this to our 8 nines of reliability or whatever we would like. So we're going to look at a specific setting motivated by a still tricky maneuver on highways, and highways being interesting because they are accepted as the autonomous driving setting that we are closest to achieving. Okay, so let's consider highway merge conflicts as the risky event. Let's assume that the vehicles can cruise just fine on the freeway. The only tricky event is merging. Okay, and we're going to consider on-ramps. We can also consider merging off. So the first thing to notice is that we don't always require supervision. If a vehicle were not to conflict with any other vehicle, as in there's no incoming traffic, then there's no need for supervision. Okay, only when there's a potential conflict, which we determine using very conservative reachability analysis, then we would like to invoke an operator, and we need to give the operator enough time to gain situational awareness. So I'm going to give just a little bit of intuition on what happens when AV adoption grows. Okay, so as there are more AVs, so the x-axis here, we have more AVs that are trying to merge. So therefore, we need more supervisors. So for a fixed number of supervisors, which is each of the colored curves here, where the reliability is going to go down. Okay, but at some point, there are so many vehicles that can provide sensing of the environment that reliability is going to go back up. This can be shown using pretty standard queuing analysis, queuing theory results. Another aspect that is interesting is as we have more AVs, AVs can sort of start to coordinate to assist with merging. Okay, so if a vehicle is merging into oncoming traffic and its nearest vehicle is an AV, then that AV can sort of, let the merging vehicle in. So this corresponds to basically taking these curves and shifting them up in terms of reliability dramatically. The key insight here is really the idea that an ounce of prevention is worth a pound of cure. So basically, if you can avoid the risky event, that's better than needing to supervise it. And the analysis boils down into something quite simple and nice in the end, which is leveraging order statistics. It basically reduces to the probability that the nearest vehicle for the incoming traffic is an autonomous vehicle. So we did some numerical experiments, and this one is, I think, pretty informative. We didn't cherry pick these numbers or anything, but we also didn't, explore this a ton. So let's consider a scenario, a reasonable amount of time to monitor and merge peak demand for a few on-ramps. And then let's consider, let's say 30% autonomous vehicles, because this is where both curves are visible. And what we see is that for some number of supervisors, the team can supervise 8 nines of cases, but this is with the cooperation. Without the cooperation, it's more like 2 nines of reliability. So this is an indication of how much of a difference this cooperation makes. This is 6 orders of magnitude difference. And then finally, how reliable is the supervision? This roughly translates to about 42 vehicles per operator to achieve the 8 nines of reliability. And just keep in mind that what we have today is a 1-to-1. Okay, so that's all I want to say about remote supervision, and that these ideas can potentially improve system reliability or cost of the system. So the last thing I want to leave you with is basically that autonomy may be sufficient, but it may not be necessary for us to make really substantial progress on sustainable roadways. And this idea of use-driven design is to first consider why we want to improve the roadways and to design for it. Seems to bring us a lot of interesting new ideas. So I hope you'll join me in this research area. Thank you very much, and I'm very happy to take some questions.
Thank you, Cathy. For the talk, let's open the stage for questions. You can either raise your hand or write in the chat, and I will repeat it for you with my nasal voice of today. So let's see. Emilio, go ahead.
Okay, yeah, so I'll start with some questions. First of all, thank you very much, Cathy, for doing this talk. Sorry I was late in joining. Now, I have a couple of questions, really thinking a little bit outside the box. So I understand the work on the eco-driving for traffic lights, right? But that assumes, in a sense, that there are traffic lights, and traffic lights are the thing that will stay, right, in a certain way. What would be the impact, or wouldn't thinking about alternatives to traffic lights be a similar impact as of driving in an eco way approaching traffic lights?
Yeah,
I'm thinking
question.
of roundabouts or just avoiding intersections, things
Yeah.
like that.
Okay, so I can tell you why I'm very enamored by the eco-driving approach in particular, and then let me try to answer your question more directly. So I am really motivated by scale. So in terms of how quickly can we roll out a solution? And what really compels me about eco-driving is that it is essentially a software update. We don't need to roll over hardware. We don't need new vehicles necessarily to be adopted. We don't need to go city by city and go through the permitting process and the process of construction, which this country is not the most, the strongest at. And so it's not that it should not be done. It's that I feel very compelled by the scalability of eco-driving for signalized intersections, especially potentially deployed through smartphone apps, and also gradually deployed through vehicle integration and integration with traffic signals and whatnot. But in terms of what could possibly be done at scale in the next few years, that is why I find this very exciting, especially from the decarbonization perspective.
Okay. I see the point, but however, I don't know about this group, right? And maybe this is not the most representative group, but how many of you guys or people who drive actually use the eco-driving mode in your car? I don't. So I don't know.
Okay,
how will you convince people that they ought to use this eco-driving mode? Whereas if you just change the structure of the roads, that people have no choice. Right?
Yes. So I think that this is it's a really important question. There is a behavioral piece, and I think that we do need to we do need a more holistic solution in terms of thinking about, should this be incentivized? Should this be required? Where does this fall into our responsibility as citizens and whatnot? So I think there's like a broader piece to this, where right now I feel like we're still tiptoeing into from the decarbonization standpoint, not just for transportation, but we are really relying on individual self-sacrifice and whatnot in terms of carbon offsets and in terms of changing one's diet and whatnot. All of this is very voluntary right now. And I think that as we get more serious about this, We are going to have many more conversations and many more expectations in terms of how do we treat the kinds of things that we can easily do, and we are just choosing not to. Maybe it will become something like, I don't know, recycling, for lack of a better example, right now. Anecdotally, when I am giving these talks, people do actually come to me and talk to me about their eco-driving modes in their cars and the different interfaces and the ones they like more and the ones they like less, and how certain interfaces that they find to be just very comfortable, they just want to eco-drive. Whereas in other cars, they don't want to eco-drive. So it's all anecdotal. And I think that we can, we can take all of this into account. We can make it a good experience. We can, if we want to value this as a society, then we can also potentially put effort into, making it worth people's time and so on. So I think I'm optimistic, but it is not a pure engineering and scientific problem.
Totally. Then, the second point was about this, this increase in safety with remote supervision, right? And you did this, case study on mergers on highway. But then, how many of the fatalities, in those 8 nines, right? So how many of those fatalities happen on mergers on highways, right? So, in a sense, what I'm wondering is all those fatalities that happen every 80 million miles or whatnot, how many of those can actually be avoided by ad hoc, on-demand, remote supervision?
I don't know specifically for merges. I'll have to look into that. I think 17% of the fatalities are on highways. But I don't know the breakdown for specifically for merges. So I'll look into that. It's a very good question. I think it will be very interesting to consider this kind of idea for intersections because that is a major source of fatalities. Okay,
guys. I don't know if you have any other questions. And I actually had to sign off. I had to run. Thank you.
Thank you, Ilio.
Thank you.
Is there any other question? Oh, there is one in the chat. So let's see. Regarding the first part of the presentation, I was wondering how the guided vehicle follows the piecewise constant control instruction in the real world.
Yeah. So I showed this, this is a real demo app, which is from the GLOSA project. So the app, I mean, there are many ways, but one way that folks have tried is through an app like this. There's like some target speed. And it could be integrated into a mapping application as well. So it could be overlaid on top of like maps.
Okay. Shiva, if this answers your question, you can follow up on the chat.
I actually don't see the question on the chat. Is the chat only sent to you?
Oh, okay, yeah. I just realized it's a direct message. Yeah, it was a direct message. I don't know why. Oh, it's a mistake. But I feel that was the question, and the answer seemed the point. Any other question?
I have a question.
Go ahead, that's it.
Yeah. Thank you for the nice talk. My question is about, I guess, the use of neural networks. So can we not come up with like more simpler heuristic policies based on, for example, the distance to the traffic light, and so on, that perform nearly as good? Or do you really find that we have to build this monster model?
Yeah, that's a really good question. So I would say that when it comes to deployment and further analysis, I would actually recommend going to simpler policies, simpler control laws. I think of reinforcement learning as an automatic procedure to come up with these control laws, because the emphasis of our work is not controller design. The emphasis of our work is actually in this higher level analysis for whether this intervention is worthwhile from, say, this climate perspective. So when it comes to more detailed work where we care about reliability of the controllers, we care about stability of the system, we care about all sorts of other properties, that then we can bring in the big hammers that have these kinds of structures built in.
Makes sense. Thanks.
Yeah.
There is another question from Jorge. There is a way to be under a policy like this and later disconnect from a practical point of view. Have you tried that?
I think I'm not understanding what is meant by disconnect from a practical point of view.
I feel I also am not sure, but I feel it's like, can you be controlled part-time, in the sense that you can switch from following the policy to not following?
Oh, I see. Yes, so I should have mentioned we're doing all sorts of work now on compliance. So right now we're assuming perfect compliance. Everyone who's given instructions is following those instructions perfectly. And so we're doing all sorts of relaxations of that to factor in reaction times and stochasticity and various forms of personalization and whatnot. So those extensions are TBD. I think it'll be fine, but we need to be rigorous about it.
All right. Any final question? Okay, Sean has a question. Is there any thought to the design of the partitions of data sets used to train the different policies? For example, do you want each partition to represent needing perhaps different or distinct control schemes?
Yeah. I will say we didn't very deliberately design the partition. We were mostly looking for a small set where it did sort of make sense that we would need somewhat different control schemes. The issue is that it takes about 4 weeks to do the training. And so we can't try too many things. So we really are using our domain knowledge to select some reasonable partition. And we have tried a few, and this is sort of what we ended up with, but further analysis and would be good.
Okay. Thank you very much, Cathy. I think this brings us to the end of the talk. It was, and also I think you gave your email in case people want to reach out for deeper questions, right?
Yep.
Yeah. It was a pleasure. Thank you again, and good luck for the next steps. Everything is very exciting, and thank you all. Thank you all for participating. I see you all next week for the next Autonomy Talk.
Thank you all.
Bye-bye. Bye-bye.